Historically, automotive safety engineering focused on the physical breakdown of electrical systems. To prevent these components from failing, the industry relied on ISO26262. This framework operates on a specific assumption. Safety risks originate from physical hardware faults or systematic software bugs. If the hardware is intact and the code executes correctly, the system is considered safe. But autonomous driving introduces a different threat vector. A vehicle emerges into blinding sunlight, and a perfectly functioning camera suddenly goes blind. The system fails. This requires a secondary framework, ISO21448, known as SOTIF, or the safety of the intended functionality. SOTIF addresses performance insufficiencies rather than physical breakages. We see this dynamic in autonomous emergency braking, or AEB systems, which rely on AI-driven sensor fusion to perceive the road and stop the car. If a vehicle's architecture treats an environmental sensor limitation, a SOTIF event, the same as a critical hardware malfunction, it will react by initiating a catastrophic, abrupt system shutdown at highway speeds. This diagram shows a standard sensor layout for an AEB system. We have a wide forward-facing field of view for the camera, paired with a narrower, longer-range cone for the radar. Cameras identify pedestrians and lane markings, but as the data indicates, their effectiveness drops in low light or when facing direct glare. Radar measures distance and velocity with high precision. However, as the reflections show, complex metallic environments can generate false positive ghost targets. Because these vulnerabilities are dictated by physics and the external environment, rather than circuit board degradation, they bypass traditional ISO 26262 safety monitoring. Therefore, autonomous architecture requires a dual-layered defense system that simultaneously maps physical fault spaces and environmental insufficiency spaces. The primary architectural challenge is real-time diagnostic separation. When a sensor's data becomes unreliable, the main electronic control unit, or ECU, must immediately determine why. This diagram illustrates the data pipeline. At the physical layer, ISO 26262 monitoring begins, tracking electrical parameters and flagging sudden voltage drops. Moving to the communication layer, the system performs cyclic redundancy checks, sequence tracking, and lockstep validation to catch dropped packets. If hardware and data transmission are healthy, the system shifts to the SOTIF layer, evaluating semantic integrity. Here, algorithms calculate a dynamic confidence score. A third layer attaches. If an image loses contrast in dense fog, the algorithm actively lowers its reliability rating. The system also runs cross-sensor inconsistency checks. A trigger event occurs when the camera identifies a pedestrian, but the radar scans the exact same coordinates and finds nothing but empty space. When physical and communication checks report no errors, but these semantic confidence checks fail, the main ECU diagnoses a SOTIF trigger. This categorization allows the vehicle to adapt its behavior without initiating a full hardware shutdown. Once an environmental trigger is confirmed, the system enforces expanded technical safety requirements, or TSRs, establishing mathematical boundaries to restrict the vehicle's physical response. The first boundary for the AEB is cross-sensor validation. Full braking authority is only granted if two independent sensor modalities verify an obstacle and exceed a predetermined confidence threshold. This equation represents the time to collision, or TTC, calculating risk using distance, relative velocity, and relative acceleration. When SOTIF triggers like radar ghosting occur, they inject variance into the inputs, causing the variables to destabilize the calculation. To prevent an overreaction, a secondary TSR rule monitors the standard deviation of these inputs. If that deviation crosses a defined threshold, the system actively invalidates the time to collision result. By mathematically constraining the AI's influence, the architecture prevents the perception system from hallucinating a phantom threat and executing an unjustified panic stop. This introduces a difficult engineering conflict, balancing high system availability with absolute safety reliability. The Doer-Checker architecture resolves this conflict by splitting processing into an asymmetric model. The primary channel is the doer, running complex deep learning algorithms responsible for multi-sensor fusion and detailed path planning. However, neural networks are opaque. Their logic is too intricate to be mathematically verified to the highest automotive safety standards. The doer is paired with the checker, which relies on deterministic logic and fundamental physics. The final piece is the selector. If the doer commands an unjustified emergency stop, The checker references actual vehicle dynamics, issuing a veto to suppress the brake command. This asymmetric redundancy allows vehicles to leverage AI perception for navigation while keeping a rigorous physics-based safety net in place. The ultimate result of this integrated monitoring is the ability to step down through a series of degraded modes, replacing the binary off-switch approach of earlier failsafe designs. This matrix maps the degradation hierarchy. The top tier uses full camera and radar fusion. When fog causes certainty failures, it steps down to a constrained radar-only mode. During a hardware fault, an isolated redundant microcontroller performs a maneuver to safely stop the vehicle. Ensuring vehicle safety requires carefully managed degradation relative to the exact condition of the hardware and the surrounding environment. Before this architecture can be deployed on a public road, safety engineers must clear the final hurdle: verification and validation. Proving the reliability of a Doer-Checker system requires large-scale virtual simulation. Engineers subject the digital models to physical fault injections and severe environmental SOTIF triggers simultaneously. The objective of SOTIF validation is to identify unknown, unsafe scenarios and mathematically migrate them into known, safe parameters. Success is quantified strictly through statistical acceptance criteria. It takes billions of simulated miles to definitively prove that the rate of unintended braking falls below the maximum acceptable threshold. Modern functional safety has evolved to integrate environmental adaptation with hardware reliability. Engineering reasoned, hierarchical judgment into machines provides the technical evidence required for autonomous deployment.